Okay, so this is a situation where you are supposed to evaluate this integral, okay, and with the help of the Dirac delta function, and yet there is no Dirac delta function in the question, as you can see, and this is on a volume of a sphere, radius r, centered at the origin. Okay, so what we're going to do is we're going to do this in two methods. The first method is basically the straightforward one. So method one. Method one is the straightforward one. Now we know because this is a volume integral. R is a vector.
What's the tau?
Tau is a volume element. It's like dV. They use d tau in this class.
And that it just didn't instead of dV?
Yes.
Oh wait, because V is for temperature.
Right. So so we know that if there's equation 199 in your book says that the gradient of this is equal to 4 pi Dirac delta function in 3D at R. Okay? So now I could replace this guy here with what we have. So now the integral becomes V 1 plus e to the minus r. And this whole thing is just 4 pi, right? Dirac delta function of r d tau. Okay, and so this, by the definition of the Dirac delta function, becomes 4 pi is a constant. It comes out. And this just picks up the value of f of x, or f of r, if you like, at r equals 0, because this is the Dirac delta function is centered at 0. So this would pick up the value of this function at 0. So this becomes f of 0, which becomes 4 pi times 1 plus e to the 0, which is 1. So this comes down to 8 pi. Okay. So this question demonstrates the power of the Dirac delta function and how you could use it to evaluate a fairly sophisticated integral, because now when I do it in the second method, you will see that it's much more work. So this is the utility of this Dirac delta function. No?
Yeah.
Right. So let's go to method 2.
It's one of those things like where you have to look for some form of it.
Yeah. Right. Exactly. Now, method 2, if I want to evaluate this integral using method 2, this relies on equation 159 in your book. So if you look at equation 159, it says it just transfers the derivative from one place to the other. I'll write it down. This is, if you go in your book to page 37. So that equation says the integral on V of f gradient A the divergence A, d tau is equal to minus V. And by the way, this just came straight from the divergence theorem. A dot. So by the way, here A is a vector. So this becomes A dot, the gradient of F, d tau, plus, so this is a volume integral, plus a surface integral, S F A dot dA. Okay. So if I apply this to the integral we have, right? If we apply this to the integral we have, let's dismantle it. We have J. Wait, where's the question? This is, let me rewrite it. So now this of 1 plus e to the minus r divergence of r over r squared d tau. Okay, so basically here, this is your F. Let me do this in a different color. This is your F, and this here is your A. Okay, and d tau is d tau. So apply the above equation to this. So you get minus the integral A, just, you know, plug in whatever there's in A. So r over r squared, right? Dotted with the gradient of F. So this is the gradient of 1 plus e to the minus r d tau. Okay, done with that. Plus, so this is a volume integral. Plus, now we're going to do the closed surface integral. F is 1 plus e to the minus r multiplied by vector A, r over r squared, dot dA. Fair enough? Okay, now let me ask you, what is the gradient of 1 plus e to the minus r? That is just the derivative, yeah?
Yeah.
Yeah, this is just minus e to the minus r in the r direction. Okay, and so if I plug that up there, I will get, so now back to the original. 1 plus e to the minus r over r squared d tau is equal to minus r over r squared, and the gradient is just minus, so this becomes a plus e to the minus r, right, in the r d tau. Oh, and there's a dot product here. So this is a dot product between two vectors. Okay, plus the other one remains the same. 1 plus e to the minus r over r squared. Okay, now here, this dot product between the two vectors, will just get you the magnitude of the first times the magnitude of the second, right? Uh, the magnitude of the first times the magnitude of the second, so it gets you um, uh, 2 over, let me see, so this is e to the minus r. Let me start from here. So this is actually, we'll stay here. So this is e to the minus r over r squared. Okay, and r dot r is just 1 because the angle between them is 0, right? D tau. Now what's d tau in spherical coordinates? If you remember, d tau in spherical coordinates is r squared sine theta dr d theta d phi. Okay, let me move this a little bit to the left because I'm not getting room here for the other one. So this became that plus, so this is a volume integral plus oh, there's a dA here that I didn't include, dot dA, right? And the r, the radial component, and the area vector, which is in the r direction, are on top of each other. They're overlaying each other. So this product will just get you magnitude of the first, magnitude of the second, which means the area, multiplied by the angle between them, which is cosine 0, which is 1. Okay. Yeah. So this becomes so just let me just include it here so you know. So dA. So this is an element area on the surface of the sphere. The radius is constant, so this is just r squared sine theta d theta d phi, right? And if I need this to be an element vector, a vector area, I would, this is just in the radial direction. So this integral becomes 1 plus e to the minus r, right, over r squared times dA is r squared. So this, you know, the dot product just becomes cosine 0 is 1. So this is r squared sine theta d theta d phi. Already? Okay, good. Let's go back to the first guy. Here, the r squared crosses out the r squared, and we will get e to the minus r dr, right? And by the way, so so this is basically a triple integral, right? Uh, so we can, since there's no sines or cosines, we can do each one separately. So theta goes from 0 to pi, d phi goes from 0 to 2 pi. Oh wait, sine theta, sorry, sine theta. And we have from 0 to r e to the minus r dr. So that's the first guy. Yeah. And the second guy, there's no integral with respect to r, so it's just a surface integral, and anything that has r can come out. You agree? So we get on the boundary of the sphere, of course, r is big R, right? So then this becomes 1 plus e to the minus r, because I'm on the boundary of the sphere, divided by r squared. And there's an r squared here, so those two cross each other out. And then again I have a surface integral, so this is sine theta d theta from 0 to pi, and d phi from 0 to 2 pi. And now I can evaluate each one separately. Sine theta is minus cosine theta from 0 to pi. This is just 2 pi, right?
That they forget to like kind of like safety to like they forget to make the whatever system they're making like fail safe.
Yeah, that's right.
You can do all this stuff with the pad, except if you accidentally have like a little bit of liquid or something or moisture on the side of the
I
screen,
don't need
it
that note.
cause your
That note needs to go away.
to get deleted.
Okay, I don't know what that one note is. It's not going away. Okay, well, let's continue, Ben, here before we lose sight of the question. Yeah. So, yeah. Already. So at the surface of the sphere, small r equals r, and here I have r squared. Shoot, come on. I have. Oh, this is so annoying. It's taking my colors away and not letting me erase. Stupid.
You think it might need think there's moisture or something in there, or there's like
Wait, let me close it and reopen it. Shit.
People when they design stuff, a lot of times they what Murphy's law is. You ever hear of Murphy's law?
Yeah. Let me see. Oh my goodness. Come on with this shit. I already entered the goddamn username. Oh, okay. Alrighty, here you go. It's not giving me the pens, but it's okay. I'll manage without them. Here we were. So we said this r on the surface of the sphere is r squared. So that means this guy goes with this guy, and we have sine theta d theta from 0 to pi, and then d phi from 0 to 2 pi. Okay. Now sine theta is minus cosine theta from 0 to pi times d phi. This will just get you 2 pi, and this will be minus e to the minus r from 0 to r. And of course this will get you a 1 plus 1, which is 2, right? 2 times 2 pi uh, 2 times 2 pi And this, if you evaluate it, it's gonna get you minus e to the minus r plus e to the 0. And here we're gonna get 1 plus e to the minus r, and sine theta again will get you 2 because it's the same thing, and this will get you 2 pi. So what we've got now is plus 4 pi into 1 minus e to the minus r, right? So if we FOIL this stuff here, we're gonna get uh, 4 pi minus 4 pi uh, e to the minus r, e to the minus r. Wait a second, and here we have 1 minus, oh, this is 1 plus e to the minus r, sorry. Yeah, and then this is just a 1, so you're gonna get plus 4 pi. I changed the goddamn color. Oh, okay, it's not changing. Great. So 4 pi plus 4 pi, right? Plus 4 pi e to the minus r. And you can see that this guy and this guy cancel out, and what do we have left? 8 pi. So the final answer is 8 pi, exactly the same exact answer we got with one line here, 8 pi. You see? So it took a lot of work without, this is the power of the Dirac delta function. It just took quite a bit of work and integration to evaluate this integral without the help of the Dirac delta function.